Okay, then I think we can start with session 5C of this year's QCrypt conference, which focuses on the topic of photonic integration. My name is Moritz. I'm very happy to chair this session today. We will have 3 talks. First one is system integration of photonic integrated circuits, photonic integrated quantum communication chips by Robert Woodward from Toshiba Europe. Second talk will be given by Li-Hang Zhang from University of Science and Technology of China, and is titled High Rate Quantum Key Distribution with Silicon Photonics. And the third talk, Realizing an Entanglement-Based Multi-User Quantum Network of Integrated Photonics by Wei-Jun Wen from Nanjing University. I'm already very much looking forward to these interesting presentations and discussions. But before starting with the talks, let me remind everyone again of the format. I guess that all of you are aware of that by now, by the end of the week. But yeah, first we will hear the 3 talks presented by the speakers back to back. And afterwards, there will be time for questions and discussions. So please feel free to write your questions in the Slack channel. And we might also, you might also raise your hand here and we can unmute you so that you can ask your question out loud and engage in the discussion. And yeah, with that, I would like to give the floor to Robert, and I'm looking forward to the talk.
Okay, thank you. I'll just share my screen. Can you see those slides?
Yes, we can see it.
Excellent, thank you. Okay, so good afternoon, everyone. And I'm going to be reporting today a brief 5-minute introduction to our recent work at Toshiba. This is from the Cambridge Research Laboratory, developing a fully chip-based quantum key distribution system. Now, first of all, I think the benefits of chip integration are fairly well known. It's a really promising way of producing systems which can be miniaturized as well as mass manufactured, which is very important to large-scale deployments. And while there's been quite a lot of work in this area already, the prior works tended to focus on proof of principles for single components or just single parts of a quantum communication system. And I think this is partly because combining everything together to make a fully chip-based system is actually very challenging. And there's a number of challenges that we list here that make this difficult, not least in making each of the chips themselves, but also in interfacing them, having the custom electronics to drive everything, and also managing things like power and heat, so thermal management, to make sure that you can have a full system that's stable and reliable, and also interface with software for delivering these keys to practical applications. And this is what we've been tackling today. So I'll briefly summarize in these 5 minutes the main chips and the system that we developed. So we start with a quantum random number generator, which provides the random numbers for basis selection. And this, you can see the chip design here, is based on an active material, indium phosphide. And this means that we can include the lasers and the modulators directly on the chip, which is very advantageous. So our random generation is based on the entropy source is spontaneous emission, and the actual design is based on interfering 2 gain switch DFB lasers. And with the various control of the chip, so things like temperature tuning and MZIs, we can get good temporal, spectral, and power balance between these lasers for good interference. And then thus we can achieve 4 gigabits per second and an output which satisfies all of the NIST requirements for ensuring good randomness. For the transmitter, we use a design known as phase sealing. And this is in order to generate time-bin encoded pulses, because we're implementing the T12 QKD protocol, which is a modified version of BB84. So we generate pairs of pulses, and we want to encode the phase between those pulses to set the basis and the information. And the nice thing with phase sealing is it removes the need for a phase modulator. The basic idea is you have light from a primary laser, which optically injection locks a secondary laser. This brings a number of benefits in terms of the laser performance, better modulation bandwidth, lower chirp, and it means we can electrically control the phase which is applied between the two pulses. So if you're interested, we have a recent, actually published this week, review article on this topic. And I know this lets us achieve gigahertz modulated coherent states for performing QKD. And this chip's also based on indium phosphide because it's got lasers on it. The final chip is our receiver. And for this, we actually use silicon nitride as our platform. The reason being that we can have lower losses, which is particularly important for your QKD receivers. So the design is shown here. You can see this large spiral here is the on-chip delay line, and this forms the basis of an interferometer, as well as things like Mach-Zehnder interferometers, the MZIs, so we can precisely compensate the different losses of the beam lines and ensure that the beam splitters are well balanced, so for good interference. We actually use an external lithium niobate phase modulator here for ease, and then the APDs are also off-chip, so the chip then feeds into these APDs for the full system. So just to show you the full system, this is everything integrated together. We paid a lot of attention to packaging and integration to make it convenient and deployable. So the QRNJ chips, even though it's the size of a fingernail, it's integrated into a butterfly package. So very conveniently used electronics packaging. And for the transmitter and the receiver, we integrate them into CFP modules. These are pluggable modules, again, widely used in telecoms. And these can just plug straight into a 1U rack-mounted box. This contains our FPGA and all of our custom PCBs for driving the full system. And in the complete system, the FPGA also performs things like sifting, synchronization, managing of feedback, and then these keys then pass to our software layer for distributing them to real-world applications. So I think that's all I've got time for in this 5 minutes. So if you want to know more, both about the performance and potential applications, please do see our talk on YouTube. And with that, I'll conclude. And thank you.
Okay, thank you very much, Robert. And yeah, with that, we can directly go on to the next talk. High-rate quantum key distribution with silicon photonics by Yifang Zhang from University of Science and Technology, China. So please.
Okay, thank you. One moment, please. Can you see my screen?
Yes, we can see it.
Okay, thank you. I'm Yifang Zhang, and I will introduce our recent work of high-rate QKD based on silicon photonic chip transmitter. So as introduced earlier, the integrated platform has the advantage of miniaturization, low cost based on mass manufacture, and easy to integrate it in common devices. And this makes it suitable for a future QKD lab work based on chip transmitters, where the detectors is placed in the city central node, and the end users can only have the chip transmitters. So based on these advantages, it's reasonable to prophesy that system integration is inevitable for future QKD developments. And there have been many pioneering works, and I'll list a few here, mostly about QKD transmitters. Still, there are some aspects in chip-based QKD, and we mainly focus on the mediocre secure key rate. And how can we push the key rate to a new level? Common methods include the higher clock rate and lower quantum bit error rate, which can both increase the key rate per second considerably. So in our implementation, we demonstrate a QKD system with a higher clock rate of 2.5 gigahertz with random modulation and a low QBA of 0.49% based on a silicon photonic transmitter and the decoy state efficient BB84 protocol. Our setup is shown in this figure, including the transmitter Alice, the fiber channel, and the detection system Bob. As the most important part, the chip transmitter is commercially fabricated and integrates all the modulators and variable attenuators. So The first point is the low QBA achieved by our modulation method. The polarization modulator is composed of two Mach-Zehnder interferometers with phase modulators on the arms and a two-dimensional grating coupler. There are two kinds of phase modulators on our chip: thermal optic modulators for the bias and carrier depletion modulators for fast modulation. The two-dimensional grating coupler at the output acts as a path-to polarization converter. Here it converts the upper arm to H and the lower arm to V. So ideally, combining all these components, this modulator can prepare arbitrary polarization states on Poincare sphere, with the first MZI changing the relative intensity and the second MZI changing the relative phase between H and V. However, there exist two imperfections on our chip. Firstly, H and V converted by the two-dimensional grating coupler is not orthogonal enough, and I substitute V as V prime. Secondly, the voltage-dependent loss of CDM introduces an additional parameter alpha in the polarization state. As a result, we cannot prepare good BB84 states by only modulating CDM2 on the first MZI or CDM3 on the second MZI alone, as shown by the red line and blue line on the sphere, with an extinction ratio of 21 dB at most. To attain better states, we modulate CDM simultaneously and use CDM2 on the first MZI to compensate the voltage-dependent loss of CDM3 accordingly, and we get a higher extinction ratio of 30 dB on the static modulation. This ensures a low QBA. Another important thing is the high clock rate. We use a homemade FPGA electronic board with a sampling rate of 10 GHz and a maximum peak-to-peak output of 7.5 watts. This is cost efficient, and the generated signals can have 4 adjustable independent levels at most, which is enough for our QKD implementation. We also did some simulation and compare between different decoy methods for a higher key rate, and we chose the 1 decoy intensity 4 encoding state protocol with a security against general attacks and the highest secure key rate in our system. For continuous QKD runs, we apply time synchronization and polarization feedback to compensate in real time the time and polarization drifts caused by the disturbance of fiber channel. As a result, we can run QKD continuously for at least 7 hours with nearly the same QBAs and same secure key rates. So in summary, we implement a high-speed, high-rate QKD experiment based on silicon photonics. Our work demonstrates the ability of chip-based QKD to achieve the same secure key rate as fiber optical systems while offering additional benefits of high robustness, miniaturization, and low cost. This is suitable for transmitters on users' hands in future QKD LED works. In the next step, a high bandwidth chip-based QKD LED work may be accomplished by combining the techniques here with other techniques such as wavelength and space multiplexing. Also, the integration of electronics and photonics on a single chip is an interesting and inevitable direction towards a higher integration level of the whole QKD system. Okay, thank you for listening.
Hey, thank you very much. And yeah, with that, we can go to the third presentation of today's session, realizing an entanglement-based multi-user quantum network with integrated photonics by Wenjin Wen from Nanjing University. So, please.
Okay, thank you so much. I hope you can see my screen.
Yes, we can see the screen.
Okay. My name is Wenjin Wen, and today I will be giving a talk entitled Realizing an Entanglement-Based Multi-User Quantum Network with Integrated Photonics. The motivation of our work originally came from these articles in 2018, where fully connected quantum network schemes have been proposed and realized based on entanglement distribution by passively filtering the entangled photon pairs into a series of slices and multiplexing without relying on trusted nodes. These fully connected network architectures are innovative and promising. And how can we improve the hardware? We believe that the quantum optical microchromes is a suitable alternative, which offers broadband dispatching range with many discrete frequency modes. And the use of source with narrow bandwidth in individual frequency modes can also make it compatible with quantum memories. Third, the chip-based quantum optical microchromes can offer stable and alignment-free options with neutral packaging technique. It is also CMOS compatible and hence it is cost-effectively. Here we realized a 4-user fully connected quantum network by employing a silicon nitride microwave resonator, which generates column-like bipartite energy time entangled states through the nonlinear process of spontaneous four-way mixing. In our photon pair source part, a continuous wave laser at the mid of 35 pumps the microwave resonator. The column-like frequency correlated photons are generated from the integrated nonlinear microwave resonator and are then allocated to 4 users to form a fully connected network by an array waveguide grating and multiple dense wavelength division multiplexer with 100 GHz spacing. Six pairs of photons are then distributed to 4 users respectively. Each user receives 3 channels and shares an entanglement state with every other user in the network. The analysis and the detection module held by every user consists of a Franzen interferometer with a time difference of 2.5 nanoseconds and a superconducting nanowire single photon detector. To characterize the microwave resonator, we measure the transmission spectrum. The inside shows the zoom-in view of a resonant mode around the channel 35 with a bandwidth of about 650 MHz. The right figure shows the free spectral range and the quality factors of each resonant mode. We obtained 128 resonance modes, and the average free spectral range is 97.8 GHz. The average Q factor is about 300,000. We then show the spectrum of the single photons emitted from our microwave resonator, that covering the entire C band, which is only limited by our spectrometer. Then we measure the dependence of the coincidence counts on the pump power for all selected 6 photon pairs, as shown in the right figure. The inside shows an instance of a histogram of the photon pairs. The coherence time and brightness state of all 6 photon pairs are shown in the table below. The data shows that the bifold coherence time are about 300 picoseconds and the bandwidth are less than 600 MHz, which proves that we have obtained individual frequency modes with narrow bandwidth. In our experiment, each user receives 3 channels and shares an entanglement state with every other user. We harness the temporal degree of freedom to identify 6 combinations of 4 users through the relative arrival times. Here we measure the 2 photon intercoincidence for 2 phase settings, 0 and pi, respectively. Each coincidence histogram has 3 peaks, revealing 3 relative arrival times due to the intrinsic nature of the Franzen interferometer. Further, we measure the 2 photon interference fringe by post-selecting each peak. The results are shown in the figure as a function of the sum of the relative phases for both central and set peaks. One can clearly see that the central peak oscillates sinusoidally with the phase, and no interference can be observed of the set peaks. From fitting, we extract the low and net visibilities, or the low visibilities are about 85%. After subtracting the measured accidental coincidence, the net visibilities are found to be about 96.7% on all pairs of users, proving entanglement in fully connected quantum network. The detected brightness, including all the insertion loss of all components, is summarized in the following table. The brightness of the mercury is proportional to the third power of the Q factor. And the use of a mercury with a high Q factor will further increase our brightness. Finally, thank you all for your listening.
Okay, thank you very much for the presentation. And yeah, with that, we can go into the question and answer session here. Right now, I don't see any question in the Slack channel yet. So yeah, please, all the listeners in the audience, please post your questions there or raise your hands here. Otherwise, in the meantime, do you guys have any questions to one another that you would like to ask?
I guess maybe I could ask a question for Li Kang. I was impressed with you. You ran your system, I think it was 2.5 gigahertz clock rate. I wonder, do you think you could push that much further? Or maybe you could comment what was the limiting factor to further clock rate increase?
Well, in our system, the electronics and also the superconducting single photon detectors limit our repetition rate. Our electronics board has only a sampling rate of 10 gigahertz, and we test it on the different repetition rates, and it can only be used at most at 2.5 gigahertz. And also we have a SPD at a timing with a timing jitter of about 100 picoseconds, and this also limits our repetition rates of lasers and modulation.
Okay, thank you.
Okay, yeah, so I have maybe a similar question to you, Robert, with regards to the phase locking and gain switching in the QKD transmitter. So what bandwidth can you achieve with this approach? What is the maximum there?
So I think it's an interesting open question, how far you can push this, but certainly if you take the base DFB lasers, commercially 10 gigahertz modulation bandwidth would be kind of the limit. There've been some interesting studies. There was something in Native Photonics earlier this year showing you can take that to the tens of gigahertz with injection locking and sort of novel feedback type techniques. So I think we're still exploring the limits of that. But one of the things that's important for QKD is we don't just want to generate pulses very fast. We need to make sure that there's no phase correlations between the pulses, because one of the the premises of using weak laser pulses is you're simulating single photons, so you need to have phase randomization. And if you try and pulse too fast without being careful about your phase correlations, you might introduce a side channel. So it's a very interesting question that we're still investigating.
Okay, thank you. And I see there's a question from the audience by Norbert Lütgenhaus.
Yeah, okay, thank you very much. Yeah, probably a similar question to what as fellow Robert just mentioned. Because it was really great, you showed these kind of imperfections that you get in the modulation and basically how you actually try to mitigate that one. Now, basically in the security proofs, do you take these imperfections into account that you have? Because I mean, we can live with imperfections typically as long as we can put some bounds on them, right? Do you do that? And basically, because there's probably a trade-off basically in how to work hard to avoid imperfections compared to the influence on the key rate. There's probably somewhere a sweet spot, right? You don't try to go for perfection. That usually doesn't work out, right? So there's a sweet spot.
Well, we actually see this imperfection as a misalignment of qubit preparation, and in fact, we test about the imperfect states before our new modulation method, and the corresponding qubit is about 2 to 3%, and that's how we account for that's how we consider the imperfection into our secure key rate, and the resulting key rate under this imperfection is less than 1/3 of our final secure key rate using the new modulation method with a QB of 0.5%.
But if I saw this correctly in your talk in the slide, it would be basically if it's a unitary, like a misalignment, then it would be just basically the ring of the four states would be still basically the big circle just tilted. But I thought it was actually displaced, or maybe I saw it wrong in your slide. Right, that's really important. So is it really still on the maximum circle, all four states sitting there? So it's really unitary equivalent, or is it like an offset of the circle?
I think you may be right. It is a lot on a ring, and maybe it is a imperfection that can be considered into misalignment. Yeah.
Yeah. Great.
Thank you for pointing out that.
Yeah, thank you. But I really like as well your presentation, because I think it's really important for us actually working on theory. It's important to see what are the imperfections that you are dealing with and how you handle it. So it's very important to see that one. Very often we see in presentations where you don't show slides like that, and then basically we are missing important input for the theory. So thank you very much for showing that one. It's important input. Thank you.
Thank you.
Okay, then I see a question by Andreas Poppe. Andreas?
Can you hear me? Sorry,
yes.
It's always the same. So one question to Wing Yun. So did I understand correctly that all the users get the signal or the correlated signal to all other users at the same time? Or do the users need to switch between the pairs they want to be connected?
Hello?
Yes.
I think let me check. Sorry. Can you repeat your question?
So if one user wants to have a key with another one, is there a special kind of setting of the network, or does each user get all the photons independently and post-select then the connection to other users? Or when I get a photon, how do I know it? Who has the partner photon?
Sorry, I'm a little.
No problem. It's okay. I will look to your long talk. Thank you.
Okay. Thank you for your.
Yeah, or maybe do on to a discussion after the session. So it's almost 4:15. I see maybe we can have one or two more questions before we have to close. I think the next one was from Sata. Sata, did I pronounce it correctly? Can you ask your question, please?
Sorry, no, I didn't have any question.
Oh, okay.
I have one question. Okay.
Yeah. Then. Yeah. Right.
I have a question to Likon. I want to ask, what's the maximum count rate of your SSPD?
Our SSPD can reach a maximum count rate of about 10 mega counts per second. Yeah.
Okay, thank you.
And if there are no further questions from the audience, then we can close this session on time. I would like to thank all the speakers again. So thank you very much for the very nice presentation, and I also enjoyed your full-length talks that are available on YouTube. So I can really recommend all the participants to watch them. And if you want to further engage with the speakers, please feel free to do so on the Meet Anyway platform provided by QCrypt. And with that, I would like to thank you and wish